This is the solution for question 20 from the trig functions revision worksheet. In this question, I'm shown two functions in the graph. The light grey is f of x and the dark grey is g of x. And I'm given 1 point to the point A, and I'm given its coordinates 36. I can fill in the values on the y-axis as a result, and looking at the x-axis then, well, this is going to be 30. This is the peak. So where I cross the x-axis next is going to be at 60, and then 90, and then 120, and I can keep filling in. And notice how the dark function, the black g of x function, starts at the origin and completes a period by the time it gets as far as 60. That means halfway along, it's cutting the axis. So actually this intersection point from g of x is actually lining up with that 30. So I've been able to fill in along the x-axis there in increments of 30 as a result. I'm asked to find the period and range of f of x. Notice so that f of x, this lighter function, completes one kind of round, if you like, of the function, or one period by 120. And looking at the range of the function then, it's going from -6 to +6. I can see, of course, that from the diagram, the midline is on the x-axis. And I can also note the amplitude, which is 6. So from all this information then, I'm going to be able to work out the function f of x. I note that the function is starting at the origin and it's moving up then to its first peak, so it's going to be a sine function. A is going to be 6 as that's the amplitude, C is going to be 0 as that's the midline. I just need to know what the B value is. I can work that out from the period. Remember that B is just 360 divided by the period of the function, so in this case that's 3. So my function is going to be 6 sine 3x, or you can say 6 sine 3x plus 0 as a nod to the midline if you like, but 6 sine 3x is fine. Next, I have to do the exact same thing for g of x. This is a period of 60 degrees, and I can see from my diagram that the range is -4, 4. It's also a sine function, so it'll be in the form a sine bx plus c. I just need to know the a, b, and c. The a is going to be the amplitude. In this case, that's 4. B is going to be 360 over the period, which is 60 in this case, giving me a B value of 6. And C, the midline I can see, is along the x-axis as before, so that's 0 again. So my function g of x this time is 4 sine 6x. The last part of the question asks us, for the section of the graph shown, find all the values of x for which f of x equals g of x. So I'm looking for the values of x at the intersection points between the two functions. Just notice they say for the section of the graph shown, that means I don't want any solutions for x that are bigger than 240, and I'll discard any that I get. And it's worth my while going through the diagram visually and just marking all those intersection points, so I've got an idea of how many to expect at the end. So I've got 1, 2, 3, next intersection point 4, 5, 6, 7, 8 and 9. So I'm expecting to get 9 solutions. Some of those solutions I can already actually see because there's going to be ones that are along the x-axis. So they're clearly going to be 0, 60, 120, 180 and 240. And I would expect those to get thrown up by my algebraic solution as I go through it. So since I know what both the functions are, I'm going to write down f of x equals to g of x. So I've got 6 sine 3x equals to 4 sine 6x. Now, the issue that I notice to begin with here is that, okay, I've got sine for both, which is probably fairly nice, but I actually have 3x and 6x. When I've got different angles, that can be problematic for the solution. So what I would like to do is I'd like to be able to change this sine 6x in some way to make some term that has 3x in it as the angle instead. Now, clearly 6x is twice 3x. So if I have a look at any of those sine 2a formulae, they could be useful for me to get my next step in my question. So I'm just making a note of that formula that sine 2a equals to 2 sine a cos a. And that's from page 14 in the log tables, with 2a being 6x and a being 3x. So I'm writing down my 6 sine 3x equals 4 times, and now I'm substituting in here for sine 6x. Okay, so now I'm going to tidy up a little bit. And there's a lot going on here. And generally I know that when I want to solve an equation, it's probably a good idea if I can to bring everything to one side and let it equal to 0 and see if I can take any further steps after that. Okay, so I noticed that there's actually a sine 3x in each term. So I'm going to factorize out the sine 3x. So I've got sine 3x bracket 6 minus 8 cos 3x equals to 0 at the end. Just to make it slightly easier to spot how to proceed, I put a bracket around the sine 3x. And this is a little bit reminiscent of the stage in quadratics when you factorise and you have your two brackets multiplying equals to 0. You're just going to let each of the brackets equals to 0. I'll just need to tidy that second answer up a little bit. So I end up with cos 3x equals to 3 over 4 and sine 3x equals to 0. Now, I want to solve these and I want to get all the solutions for them, and I just have to watch out for the fact that I am going to have to look for reference angles, but also take into account, because of this coefficient on the x here, I'm going to have to take account of the plus n360, because there'll be multiple possible answers, and that'll always happen when you've got a 3 or any coefficient in there in front of the x and the angle. So calculating reference angles here, and I suppose in the case of the sine 3x equals to 0, I'm really looking for the main angles on the axes that give me a sine value of 0. And in this case, that's going to be, well, both 0 degrees and 180 degrees. So what I'm going to have to do, and you can find those values, by the way, in the log tables, what I'm going to have to do is say, first of all, 3x equals 0 plus n360. And then I'm dividing by 3 to get x equals 0 plus n120. I do the same thing with the 180. In that case, 3x equals 180 plus n360, again, divide across by 3, x equals 60 plus n120. I'm not finished with these two solutions yet. I'm going to have to put n values in for them in a minute, but I'm going to save that and do that for everything at the end. Okay, so now I've also got cos 3x equals to 3 over 4. Clearly here I've got a positive cos value, so I'm going to have to think about which quadrants I should be looking at. And in this case, that's going to be the first and the fourth quadrant. Using my calculator to get the reference angle in the first quadrant, I get 41.4 degrees. And in the fourth quadrant, I get 318.6 degrees. Now I'm going to have to do the same thing with these guys that I did over here with my 0 and 180. So 3x equals and then add n 360. That's because, of course, again, of the coefficient that I have there on my angle. So first of all, 3x equals 41.4 plus n 360. I'm going to divide that by 3, which will give me x equals 13.8 plus n 120. And the exact same for my fourth quadrant solution. Again, divide by 3. And in this case, I've just chosen to round to one decimal place, but obviously just keep an eye for the question in case they specify a particular number of decimals that they require. So now we're very nearly there. We have these 4 equations that we're going to work off. We now have to just sub in our n values. Don't forget, we always start with n equals 0, and we use as many n values as indicated by the coefficient of x. So in this case, 3 values, so n equals 0, n equals 1, n equals 2 into all 4 of these guys. Starting off with these 2 equations, I'm going to get an x equals 13.8, 133.8, 253.8, and then over to my other equation over there, and subbing in the same values, I get another 3 solutions. Okay, so I mustn't forget about these guys down here now. I have to go back and put in my n's for them also. And I'll get 3 solutions for each of those. And I have the solutions worked out then for those guys as well. Now, at this point, it's really important that I go back and read what I said in the question, find all the values of x for the section of the graph shown. So we can see, if we look back up to our diagram again, that we only went as far as 240 on the graph. That means any values that we're after getting over 240 can be disregarded, although the 240 itself can be kept. Earlier in the question, we noted that we should have 9 solutions. Just to quickly check now, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9 to correspond with the 9 points that we marked in our diagram to begin with. And it'd be no harm to just go back and do a quick check to see if all the ones that are supposed to be there are there. So for example, those points that are along on the x-axis, we can see that we've got the 0, definitely. The 60 was the next one. We've got a 120, that's accounted for, a 180 and a 240. So they're all fine, they're all there. And then if I look at my other values and just do a visual kind of check to see do they look reasonable as answers. So this looks like it's about a third, maybe a bit of a less than third of the way to 30. So 13.8 seems reasonable for that. The next one along the way here is 106.2. So this would be for this point down here. And again, that looks like it's a reasonable answer for that. Then we've got 133.8. So again, that looks like it's about at that point on the diagram. And finally 226.2, which would be this point down here, which again looks reasonable given the values that we have in our graph. There's a lot going on in that question in terms of solving for the values of all of those angles. But even if you got stymied on the main calculation part of the question, you should have had enough information at the beginning to be able to figure out at least these points of intersection along the x-axis and gain some attempt marks via that.